This video reviews one of the most fundamental principles or tools in statistics, the central limit theorem. Many statistical analyses in some way involve sampling distributions of the mean. Remember, the sampling distribution of the mean is the distribution we would get if we sampled a population an infinite number of times using the same sample size. Calculated the mean for each of those samples, and then created a frequency distribution of all of those means. Like I said, we use the sampling distribution of the means a lot, and we use it in ways that assume it's normally distributed. For example, calculating the standard error of the mean, and then seeing whether our sample average is above or below some value. Now, students will often wonder, but what if the population is not normally distributed? What if the population is highly skewed? Won't that mean, no pun intended, that the sampling distribution of the means is also not normally distributed? The answer is no. Sampling distribution of means tend towards a normal shape as the sample size becomes larger, regardless of the underlying shape of the distribution of individual scores. We call this the central limit theorem. The larger the sample, the closer to normal the sampling distribution of means will be, regardless of the shape of the original data. How close is close enough? You'll typically see statisticians talk about a sample size of 30 being sufficient that one can assume the sampling distribution of the means is normal. And the beauty and power of the central limit theorem is that by doing so, we can now use the normal curve for many of the analyses where we will be comparing and testing sample means. Again, regardless of the shape of the original data. But don't just take my word for it. Let's look at some simulation data I made that shows the central limit theorem in action. I first created a population with scores on a scale that ranges from 1 to 10. Here's the distribution of the raw scores, and you can see that it's very positively skewed, with 3/4 of the scores ranging from 1 to 3. Now, because these are raw individual scores, you can think of it as reflecting a distribution of sample means where the size of our sample, n, is equal to 1 person. But what would it look like if we took 10,000 samples of 2 students, calculated the mean for those 2 students, and graphed those means? Well, I did that, and here's what I found. Notice that it's still very skewed, but a little less extreme. We also have more possible values because we're plotting the mean of 2 scores, so we can have a mean of 2.5 or 5.5. Now, what if our sample size were doubled to 4 and we collected 10,000 new samples? Here we go. Still skewed, but starting to look less so. What if our sample size were doubled to 8 and we took 10,000 new samples? With n equals 8, we see it's getting closer to normal. What if we double again to n equals 16? Okay, let's double again to n equals 32. Here we can see the sampling distribution looks close to normal. Yeah, it's a little bumpy, but that's still because it's based on 10,000 random samples of 32 people. But you can see how the sampling distribution of the mean looks fairly normal by the time we hit a sample size around 30, even though the original population was highly skewed. That's what the central limit theorem is all about. Now, while this video is about the central limit theorem, I don't want to miss the opportunity to use this simulated data to illustrate the impact of sample size on the standard error of the mean. Remember, the standard error of the mean is the standard deviation of sampling distributions just like these. And what happens to the standard error as the sample size gets larger? It gets smaller. And notice That's exactly what's been happening to the distribution of sample means in our simulations. As our sample sizes have gotten larger, the standard error, how spread out those sample means are, has gotten smaller and smaller and smaller. Okay, let's keep going. So here's the distribution when n was 32. What does it look like at n equals 64? Here's 64. Now, how about n equals 128? Here's the distribution of 10,000 random samples with n equals 128. Notice that the spread of our distribution of the means, the standard error of the mean, is getting smaller each time. And in regards to the central limit theorem, notice that the sampling distribution of these 10,000 means is getting more and more normal. So that's the central limit theorem. Sampling distributions of the mean tend towards a normal shape as the sample size gets larger, regardless of the underlying shape of the raw scores in the population. The larger the sample, the closer to normal the sampling distribution of the mean will be, with a sample size of 30 often seen as large enough that we can assume it's normally distributed for our analyses. That's a very useful quality of sampling means. Okay? Take care.